Thank you for joining, everybody. Welcome to the Women in Data Science Conference. We're super excited to have you here today. Today, I'm lucky enough to introduce Christy Heaton, who is here with us today from Floyd Snider. She's a data scientist there. And with that, I will turn it over to you, Christy.
Okay. See my screen. Okay. Okay. Hi, everyone. Thank you for having me. Today, I'm going to be talking about analyzing environmental contamination with Python. My name is Christy Heaton. My pronouns are she, her. Here are my socials. I'll also show them again at the end, and my Twitter handle is at the bottom of every slide. I am a Geographic Information Systems, or GIS, analyst at Floyd Snider, which is an environmental consulting firm in Seattle. I work primarily with geographic data and perform analysis and create maps and other data visualizations, typically depicting the extent of chemical results. And Python is my go-to programming language for data prep, analysis, and visualization, which at work I use in conjunction with the traditional mapping software. And I'm also involved in the local open source mapping and Python communities as a co-organizer of MapTime Seattle and PyLadies Seattle. Okay, so what is environmental contamination? Environmental contamination is the existence of a hazardous substance in a quantity and location in which it may be hazardous to the environment or to public health and safety. Chemicals in unsafe quantities can be introduced to an environment in a variety of ways. So a few examples are like from industrial activities or mismanaged landfills. Environmental consulting firms like the company I work for do a number of things related to helping clients assure that their property is safe and in compliance with laws and regulations. But what I'm going to be focusing on is data analysis and data visualization that helps the scientists that I work with to better understand the conditions at a site. The types of questions the scientists will have about the conditions of a site are multidimensional, covering space, time, and depth. So some questions they may have are, is there contamination at a site? In other words, are there chemical concentrations found at the site above the determined safe levels? If there is contamination, what chemicals make up that contamination? How deep does the contamination go? Is it changing or moving or changing form in some way over time? Data that we use for analysis is obtained from field staff going to a site and collecting samples, which go to a laboratory and then get returned as lab reports that then get validated and QC'd and are eventually available in a database or some type of tabular format. And from there, we can use Python to group and categorize data, compare chemical concentrations against levels that are determined safe, and create maps and charts, all in a way that is accurate, consistent, and reproducible. And from there, decisions will be made on the best methods to clean up the site if needed. So I'm going to go into a demo, and all my code is on my GitHub. Switch over to my notebook now. Okay, so for this example, I'm using some data that came from the Environmental Information Management System, which is run by the Washington State Department of Ecology. They have a ton of environmental data. And the project I chose is a small historical dry cleaner site in Bothell, Washington. So the way dry cleaners work, instead of cleaning clothes with water, they clean them with a chemical solvent that they then remove from the clothes. But that solvent can be hazardous if introduced to the environment because it's spilled somehow. So we work on some historical dry cleaning sites and cleaning them up. But like nowadays, there's practices in place to reduce spills from dry cleaning activities, but historical dry cleaning spills can be a hazard today. But that's just some context about dry cleaning sites. Don't worry too much about this data set. It's just a sample data set for me to show you some of the technology I use to analyze environmental data. Okay, so we'll import some important libraries. We'll use pandas for data analysis and manipulation. GeoPandas is geographically enabled pandas, which I use a lot since I make maps a lot. So we'll use GeoPandas for mapping and geographic analysis. We'll use Folium, which is the Python wrapper around JavaScript's leaflet library for interactive maps. Matplotlib is good for non-geographic visualizations, but I don't think we'll get into those today, but they're in kind of my extended analysis. And NumPy is used in an aggregation function. So our data is currently in a CSV file, which I downloaded from Ecology database. So we'll load that in as a pandas data frame. Now we'll do some preliminary cleanup and make a preliminary map. So first I want to filter out groundwater data. So this particular project has data, chemical results taken from soil and groundwater. So soil is the kind of dirt in the ground, and groundwater is the water you find underground in the cracks and spaces. Groundwater can be sampled via monitoring wells, which are semi-permanent structures that you can sample in over time to get results over time from the same location. And groundwater can also be sampled along with a soil event as kind of a one-off groundwater sample. But you would never want to throw groundwater and soil results like together and handle them the same way, because they are in different units and they're different media. So I'm going to filter out only groundwater data for this particular analysis. Next, we haven't looked at our data yet, but I've gone through and seen there's a lot of columns in our data that we don't need. So I've gone and just picked out the columns that are relevant to our analysis and keep only those columns. And then we have some coordinate columns here, which are going to be crucial to making maps with this data. But these columns are really long. It's great that I know that they're in decimal degrees, but now that I know that, I'm going to go ahead and shorten them to just latitude, lat, and long. And we can look now at the first few rows of our data. We have location ID, it's the type of result for the oxygen, for example, pH. We're actually not going to use any of these. These just happen to be at the top of the data set. And we have lat, long, shortened columns. So at this point, we can turn our data frame into a geodata frame to prepare for mapping. So to do that, we will call the geodata frame method on the data frame, pass in the data frame, assign the geometry to be the longitude and latitude columns. And the CRS stands for Coordinate Reference System. So there are actually a lot of different coordinate systems to identify locations on the Earth. Latitude and longitude is associated with this particular code. So I need to say this is the system that they're in. And GeoPandas does not support date-time columns very well. So I'm going to preemptively convert our date column into a string. And I'm also going to filter out only data that is from 2014 or later. Look at the first few rows. Now we're looking at a geodata frame. The only difference is now we have a geometry column and a string format for the date. To quickly prepare these locations for mapping, and so we can kind of see where we are, I'm going to create a version that just has the location ID and geometry dropping duplicates, which will give us a simple data frame with just one record per location. And then oftentimes when I'm doing analysis, there are some important areas to consider, like the parcel boundary or an area of concern. So these are just example areas that I made. They're GeoJSON files, but they can come in easily as a GeoPandas data frame. So I have an area of concern and a site area just to give our map some context. And then you can make a map, an interactive map, pretty easily with the latest version of GeoPandas. On the geodata frame called the explore method, you can pass in the base map tiles you want to use and the color you want your layer to appear. If you want to show multiple layers on the same map, you set the first layer to a variable, which is the map object. And then any other layers you want to add on top of it, you pass in the map object. So we'll add our site area, our area of concern, and then these simplified location dots to our map. And you can see the map right here in the notebook. If we zoom way out, I can see that we are in Bothell. And we can also just see our site area here and our area of concern. And then this is where we have data, groundwater data, or at these little blue locations. So now let's check if there is contamination at the site. So back in our main data table. So first I want to define the chemicals of concern, and these are chemicals associated with historical dry cleaning activities. Create a list of just those chemicals of concern. And then here I can filter out only rows that are related to one of these chemicals of concern. Then my chemical names are really long, and I'm going to be using these names in maps and figures. So I'm going to create abbreviated versions of each of these chemicals to use going forward. I'm going to put them in a column called ABBR, abbreviation. And I'm going to set these abbreviated values in my abbreviation column so I can use those for the chemical names going forward. Then when we are, looking at data, this could have come from various sources. It's always great to check that your results are consistent and they're in what the units that you expect. So at this point, I've filtered my data quite a bit, and I can check the unique values in my result value units column and make sure they're all the same, and they're all in micrograms per liter, so that's good. Now, when data gets analyzed by a laboratory, so we're talking about cleanup levels. So every chemical is not necessarily dangerous unless it exceeds a certain concentration. And these values vary depending on where you are and if an area is expected to come into contact with humans, and there's other factors. So the cleanup levels these are the levels of each chemical that are determined to be safe in this particular area, are listed out here in micrograms per liter, so the same units that our data is in. So these are the values we want to check against. And then when a lab is analyzing data, they can only detect data and chemical results down to a certain value. They could never say, like, there's 0 amount of a chemical here. All they can say is, we can't detect it. So if they can't detect a chemical, they will provide you with the minimum detectable value that they can provide. And they'll also give the data a qualifier. So our data has this result data qualifier column, and if that value is U, then the value they're giving you is the minimum detectable value. And that value is likely higher than the actual result. It's definitely approximate. So the way you can handle data like that, you can handle it different ways. But for this example, I'm going to set any result that has a qualifier of U to -1, just so that it will never exceed a cleanup level, because sometimes they can't detect, especially if it's historical data, lab didn't have high-tech technology, that minimum detectable value could be higher than a cleanup level, but it doesn't make sense to say that it's higher because it's so approximate. So preemptively turning any undetected results to -1 before we check for exceedance. Now we can check the exceedance factor of each result. So we want to know, does a result exceed? And if it does exceed, does it exceed by 1 time, 2 times, 10 times? That's going to give us a better idea of the contamination at the site. So to get that, we'll loop through our data. The cleanup level will be whatever the current chemicals cleanup level is assigned up here. And then we'll check if it exceeds that cleanup level by 1 time, by 2 times, by 10 times. Whatever the exceedance factor is going to end up in an exceedance factor column. So we'll have the exceedance factor for each result in our table. Okay, we can look at our table at this point and see that it's all the same as before. But over here, we have our abbreviated chemical name. We have the results, which in this case, these were non-detected results. They have the U qualifier, so they got a -1 in their result. And their exceedance factor is 0. These are the first few rows. So the better way to check for contamination is to check for the maximum exceedance factor. And if it's anything higher than 0, then there's definitely contamination in this data set. And our highest exceedance factor is 10. So there we can say that there is contamination at the site. Okay, so let's dig deeper into what is the extent of contamination and what is the extent of contamination for each chemical of concern. So at this point, our data set still has multiple results, multiple records for a location and a chemical with different results over time, most likely. But I just want to look at the maximum result per chemical per location. So this line of code will filter out only the maximum results. Then, because we want to handle each chemical differently, I need to prepare by creating a dictionary where the keys are the chemical names and the values are the geodata frames that are associated with only that chemical, so that I can loop through each chemical. So this creates that dictionary of key value pairs where the key is the chemical name and the value is the geodata frame with that chemical. Now we can create an interactive map of the results with a different layer for each chemical. So to do that, I will, using the Folium as opposed to just GeoPandas Explore, because this allows me to customize a little bit more. In this case, it's allowing me to customize the layer control. So I'm going to create a map object using Folium. We'll pass in the initial location of the interactive map, which is a set of coordinates that I've chosen to center on our area. The zoom start is the level of zoom that we're just starting on. You can always zoom in and out after the fact, but it's going to start on a fairly zoomed in number of 17. Zooms get, as they zoom out, the number is lower. And we're going to use our the base map that we've been using, kind of a black and white base map. So now we have that map object. We can add our site area using the GeoPandas Explore method, pass in the map object, give it some customizations. And same thing with our area of concern, pass in the map object, and we're adding names to these so that they appear in the layer control appropriately. Now we can add a layer for each of our chemicals, loop through our dictionary of geodata frames. Our current geodata frame is going to be the one associated with the current COC. Then we'll run the explore method, pass in the map object. The name, which is going to appear in the layer control, is going to be the abbreviation, which we can pull from the first location, the first record of each geodata frame. We'll pass in a color scheme. Show equals false is going to have these turned off by default because we want to look at them individually, intentionally, one at a time. We want to color these locations by the exceedance factor. So I'll pass in the exceedance factor as the color by column. We're going to make a customized binning scheme because we know there are only going to be 0, 1, 2, and 10 values in our exceedance factor column. So very clearly stating those are the bins. We want our marker size to be a 6-point radius. And I'm going to add a customized legend text that has information very specific to what each of our exceedance factors mean. And a tooltip where I can highlight just the column names I want to appear on a tooltip. And we'll add our layer control and some customizations. Now I could view this map here in the Jupyter Notebook, but since it's kind of more complex, I'm going to save it as an HTML file and look at it full screen. So I've saved it and open it in another tab.
Christy, I wanted to let you know we're getting close to the end of the session. So any attendees who have questions, feel free to get them into the Q&A before we finish up here in the next minute and take those. Thank you.
Absolutely. Okay, so here's the final map. It's got our site area, our area of concern, our legend down here, And then if I hover over the layer control, you can see we can toggle off any of these layers. And here are our chemical results. So I can turn these on one by one, and anything that's darker shade than yellow basically is contamination. I can take a look at each chemical contamination, and I can hover over to see the relevant column names and so on. So this is now an HTML file that I could send to a colleague who doesn't need to know anything about Python or GIS really, and they'll know that all of this data has been prepped, cleaned. It's really ready for them to use for decision making on how to clean up this site from here on out.
Thank you so much, Christy. That's really cool. I like the visual. It's very simple for people to understand.
Yeah.
I want to thank you for your awesome presentation today. And we're going to head over to Q&A if anybody has any questions. I know I had one to start, which is how many layers can you add to a map?
I think you can add as many as you want, but if you're viewing it in the notebook, you'll sometimes run into, if you have too many points, they just won't show up within the notebook. But if you save it as an HTML file, then it will show up. So I think it's like there are some limitations, especially if viewing in Jupyter Notebook. But
there's another question. Can you explain the difference between GeoPandas and Folium?
Yeah, GeoPandas is more like it's just very similar to pandas, except that you can do geographic mapping and spatial analysis with it. Whereas, was it Folium? Folium is more about making an interactive map. So GeoPandas is like munging data, spatial analysis. Folium is just building an interactive map with that data.
Very cool. And what are you using to save the HTML was another question.
So mapobject.save, and then the path you want to save to.
Very cool. We've got about a minute left. If there's any additional questions, we can post Christy's email for you guys to follow up after the session. Yeah, I'm curious, what has been your most rewarding project?
You know, I love anything where I can develop new methods and really make complex data munging tasks really fast and accurate. So sometimes the actual output isn't necessarily that interesting, but I know like what went into it and just like how much is going on behind the scenes for my colleagues to just look at and understand.
Very cool.
They're on my GitHub. If anyone wants to look at the notebook, there's some extended features that I just didn't have time to get into today that look at analyzing data at different depths and over time.
And then the last question I think we have time for is their workflow the same each time you receive a contamination report from a site, or are there differences, caveats each time?
A lot of code can be reused for different projects, but there's always something different. So I really like to keep projects separate just because there is always some little difference in how we're handling data or, different areas of concern and things like that.
Wonderful.
So, I would say there are differences each time, but for the most part, you can reuse a lot of code in different projects.
Very cool. This is really neat. It's fun to see the visuals and how they all come together. I think we are getting to the end of our session here. I've posted Christy's information here in the session. And again, the recordings will be available after the event. So thanks so much for joining today. We hope to see you in other sessions. And thank you, Christy, again, for a really cool presentation today and your time.
Thank you.
Thank you, everyone.